machine to think like a man, then what you need to do? You have to, it is not a magic that you are commanding something to your machine and machine will do something. It is the mathematics running behind within your machine. So that mathematics you have to design, okay? The thing is that it is an optimization in that sense. For example, if you have a machine that is used to recognize a face, for example, then what you will do? If we you have to train your machine, what we usually do in practice, in our case, if you see someone, for example, once in your life, it is very difficult for you to remember his face, isn't it?
Yes, sir.
But if you see that person, for example, for years together, then after a huge pause, still you can remember him. For this reason, actually, you need to train your brain in such a way that whenever that person is coming to you, I will acquire the image, then it will be compared with what is stored there in your brain previously, then it will take the decision accordingly. The similar thing is there. Okay, in that case, what will happen? An iterative process is always going on inside your machine. Okay, so that your machine should be learned or trained. Then, whenever a new data will be coming, then you have to compare this with your learned something. Then you have to minimize the error. While you are minimizing the error, then the optimization or some minimization or maximization problem will be involved in every step of your learning. So these are the things you will gradually learn in your higher order courses. But here we will start with a very simple problem. Then we will conclude our lecture. And I hope that if you want to move further on top of it, you can do that. You will be thinking, but the problem is actually there exist many algorithms. Actually, some algorithms are heuristic type, or in other algorithms are bio-inspired. Okay, the heuristic type means it will not follow a definite mathematical something, but still you can replicate or resemble it with some physical phenomena naturally occurring, so that you can solve your problem. In other cases, you can take help of your mathematics, so that your mathematics will tell you how to find the maximum or minimum values. So in this, at the beginning, okay, you will see in chapter 13 of your book, some descriptions are there. But before going to that, I want to share uh, your whiteboard to start with a known problem that you are encountering from the very beginning of your course. For example, if our optimization problem is something like that, to find the minimum or maximum values of a function, you see that that function we sometimes call objective function or cost function, that cost function should be minimized or maximized. So that function can be a function of one variable, or it can be a function of many, many variables. Okay, let me give you an example of a one variable cost function. For example, you have already learned it in your first year. Have you learned, for example, your maximum power transfer theorem in your
Yes,
first
sir.
year?
Yes, sir.
Okay, fine. What is that? What was the objective of that theorem?
Sir, to draw out the maximum power across the load.
To draw the maximum power across the load, what particular condition should be satisfied?
So the load resistance should be equal to the Thevenin resistance.
Load resistance should be equal to the Thevenin resistance. Very good. Actually, the thing is that whenever we are designing an electrical system that is actually valid for DC electrical circuit only, but for alternating cases, we have to have our King complex. For this reason, a conjugate meshing will be needed. So if you have our thing that is DC, say, and we design a network to feed a load, okay, your network can be a simple, okay, that means if we represent this network as a network that is designed to feed that load, then what will happen? Your load can vary. If you change the value of load, the power across the load will also vary, isn't it?
Yes, sir.
Yes, sir.
Then if we just plot that power, plot that load power with the value of the load, it will take the shape of something like this, isn't it?
Yes, sir.
Okay. Then you see that the power is reaching at a value maximum. Consider that that value of R is equal to RL max. And you are receiving a power there that is UP max, isn't it? You said that that can be derived experimentally. If you can have this curve, we can find it. Or we can, how did you find it actually? Because you said that this part of the network can be represented by a Thevenin equivalent, isn't it? The
Yes,
Thevenin
sir.
equivalent is nothing, but you are representing your network by a non-ideal or practical source, isn't it? This is your RL. That part of your network is working as a source for the load, isn't it, to feed the load?
Yes, sir.
Yes, sir.
Then, as you said that your load will receive maximum power when your load resistance is equal to the Thevenin resistance of that network. So how did you know that?
Sir, we had
Sir, expression থেকে
differentiated.
differentiate করা হয়েছে, sir. Difference, first derivative will be equal to 0.
First derivative of what?
Sir, the power equation
Power equation.
with respect to R.
Very, very good. Okay. Now you know that your power equation here, your P can be something like this. Okay. P is equal to you see I square into RL, isn't it? I means your VTH divided by RTH by RL. This is your I squared multiplied by RL. This is what your power equation, isn't it?
Yes, sir.
Yes, sir.
And you see that in your power equation, actually, you have a variable. Which one is variable?
RL.
RL.
RL. Very good. So your power P is actually the function of RL, isn't it?
Yes, sir.
Okay, then we take the derivative and set it equal to 0. And that will give you an equation that you can easily solve to obtain RL is equal to RTH, isn't it?
Yes, sir.
Yes, sir.
Okay, very good. What is the logic of setting this thing equal to 0?
Sir, the
maximum
logic is in the
derivative
maximum
is-
point, the slope will be 0.
Yes, very good. So you know many things related to you optimization or maximization problem. Very good. You see that actually in your book you will see, because I am not sharing the text. I will share the text at some point, but many things are there already discussed in your book that we are also discussing here. Okay. So you see that at the maximum point, you see your curve is flat, isn't it? Is it not flat?
Yes, sir. Yes, sir.
If it is flat, then slope of your curve would be equal to 0. And that will give you the condition. So in that case, your key thing is what? This is what the function you have to derive. Okay, this function we call objective function. In some cases, this is called cost function in optimization jargon. Okay. So once this is there, fine. So now, if you do not have any idea about, for example, about the nature of variation of your curve, sometimes you may be confused because your curve can be something like this. If you have a curve something like this, at the same point, you may have the similar problem, isn't it? The curve would be flat.
Yes, sir.
And what is the relationship between these two curves? Is it not minus P?
Yes, sir.
Yes, sir.
That means if we have a function in general, then what we can say, if we have a function fx Then if we set another function f minus x, then if this is a maximization problem, then what will happen? It becomes a minimization problem, isn't it?
Yes, sir.
Yes, sir.
So sometimes we need to need that transformation, because later if you want to proceed further with your higher studies or research, you will see that nowadays we use some bioaerospace type algorithm like genetic algorithm, where your cost functions should be calculated in a reverse way, so that a maximization problem can be transferred into minimization problem by just transforming the objective or cost function. Now the thing is that what I was discussing about, that if we have our fx, and if we know the behavior of the fx with respect to x, then we can find that whether we are calculating the maximum or minimum values. But if we don't have this thing with us, then how to ascertain that? Because we have two tests. One is called necessary, another is sufficient. Our necessary condition is what? Flatness should be tested. But in sufficient condition, just to substantiate that prediction, we need another condition, okay, just to substantiate it. What is that condition? That whether we are reaching actually the minimum or maximum.
Sir, we will have to double differentiate.
You have to take a second derivative, isn't it?
Yes,
And
sir.
what information of second derivative is important?
স্যার সেকেন্ড ডেরিভেটিভে স্যার ভ্যালুটা যদি স্যার মাইনাস হয় তাহলে স্যার হচ্ছে ম্যাক্সিমাম, আর যদি প্লাস হয় তাহলে স্যার মিনিমাম।
Okay. Yes, you are right. But have you ever checked it?
Yes, sir. In college.
Yes, sir.
Yes, sir.
Okay, you checked it in college, but mathematically, can you prove it? That second derivative, sign of second derivative is a necessary test for maximization or minimization?
স্যার এগুলো স্যার অ্যাডমিশন টাইমে চেক করেছিলাম স্যার, যে সাইনের ফাংশন তারপর কসের ফাংশন নিয়ে হতো।
Okay, if you have a function already given, that can be checked, okay, no problem. But mathematically, actually, if you want to find it, because this simple one-dimensional strategy can be replicated for multidimensional cases also. So the basic is, let us consider our general perspective. X, this is your fx. If we plot this, you will see that we are reaching at a maximum value. At a point, say S asterisk, that point we call it a maximizer. Okay, and that point is sometimes called a stationary point. So at that point, actually your curve becomes flat. In order to test this, let us perturb that maximizer, okay, in such a way that we'll have another x value. That x value can be x asterisk plus delta, plus minus delta. Okay, you can perturb in either direction, okay, either there or there. Okay, this can be your delta, and this is also delta. Then our logic is what? Your fx should be less than fx asterisk, isn't it? For maximization.
Yes, sir.
Okay. Then in order to just test it by mathematically, what you can do, let us consider plus sign only, okay? Then we have to approximate the value of fx with the help of this function value by using Taylor series. That means your fx is equal to fs asterisk plus delta. We are considering the right point only. Then that will be equal to what? It will be equal to f asterisk plus delta into f prime f asterisk plus delta square by factorial 2 f double prime f asterisk. And you can have your third derivative there, factorial 3 f asterisk, isn't it?
Yes, sir.
Yes, sir.
Okay. Now tell me, at the point of maximum or minimum, this is equal to 0. Is it not equal to 0?
Yes, sir.
because
sir.
this is the first derivative. It is 0. This is the one condition that already we already have been has been satisfied. And now you have this function value, and you have consider your second derivative only. Then if this term in the second derivative is plus, then it will be added with f asterisk, isn't it? That means your value will be equal to f asterisk plus delta square by factorial 2 f double prime s asterisk. Isn't not this becomes nearly equal to f? Is it okay?
Yes,
Yes,
sir.
sir.
In that case, what will happen? Is that condition will be satisfied?
No, sir.
Sir, it's
Because
a right point, so it won't be satisfied.
even a left point as well as your right point, in both the cases, you see that if we take this thing, it will not be satisfied. Okay. So the thing is that if we have, in your right point, because this is a square, okay, the negative effect will be eliminated. You got my point. If we take, for
Yes, sir.
example, probably you are asking this thing, okay, x factorial minus delta. In that case, actually, second derivative term will always be positive because delta square is there, isn't it? But this
Yes, sir.
sign is very important. If in both the cases, if your plus sign is there, that means your fx will be greater than fx asterisk because you have added a term there. So you are not reaching at the maximum. So that should be negative then. If it is negative, then this condition will be satisfied. You understand the point why the negative sign of
Yes,
second
sir.
derivative will be needed then?
Yes, sir.
Okay. Now the condition is that in some cases, this can be 0. Second derivative can also be 0. Have you encountered this situation in your earlier classes that even your second derivative is becoming 0?
Sir, it's a straight line like situation.
Whatever may be the situation, you can gauge it that second derivative will be 0 when? If your first derivative, if your second derivative is 0 means you are dealing with a curve, that curve becomes flat after first derivative, okay? You got my point?
Yes, sir.
Yes, sir.
So if it is flat, then your slope of the second derivative curve will be equal. So in that case, using the same logic, you can proceed with your third derivative. The sign of your third derivative can be a factor then, okay? But some other tests are there that is actually made by using some higher order mathematics, but at this introductory level, you can consider this thing is sufficient for you, okay? But in this case, you can proceed to find or ascertain whether you are maximum or in a minimum, okay? Now the question comes here. The central problem is what? You have to find the value of your design variable at which you are obtaining your maximum or minimum values. In finding this thing, you may have your function, not something like this. You can have your function varying in this way. Something like this. That means many minimas are there and many maximas are there. Isn't it?
Yes, sir.
These are actually not the actual thing, okay? In the upper cases, you can call them local. And these are also local minima. And globally, you are obtaining a minima, isn't it? So if you
Yes,
want to find it actually, this is a problem, okay? One thing is that this is actually a real problem in solving optimization problem. Then what you can do, if you have a single dimensional problem, it can be handled easily, a bit easily, I would say, not exactly the same thing. You can do it probably in three possible ways. First, the behavior of the function, okay, can be estimated or plotted by using some plotting function. You can plot it, calculate it, and see how your maxima and minima are changing. Or you find an optima based on widely varying and perhaps randomly generated starting point. What you can do, you can find a randomly generated point, for example, say find the value here, here. Then you compare the value gradually. Then what will happen if you have a range of, for example, data over which you have to find your global maximum, then what you can do? Can't you find some incremental search algorithm just to compare the values in such a way that you will find a true maximum there? It is something like that, finding the maximum value of an array.
Yes,
Have
sir.
you
Yes, sir.
yeah. So in this way, you can do that. Or another issue is that if we are, for example, obtaining a value, for example, say here, say for maximum, okay, we are obtaining a value here for maximum, but we do not know yet whether this point is actual global maximum or not. Then you can part up the value, okay, in either direction. Then what will happen if we are going, for example, to another point that value is higher than this value, then you can think that this could be a value that is a global, but still it is not global, but that maximum value is higher than your previous maximum one, okay? Then again, you part of it. If you part of it and your calculation is repeatedly coming here again, then you can conclude that this could be your global maximum. So in this way, actually, it is done. But finding the value are actually very similar to finding the root or something like this, okay? The thing is that if we have, for example, a function, okay, you can use a bracketing technique there. Say we are having bracketing it. Say this is your lower value, this is your upper value. Then what will happen? You can choose, for example, you can shrink, for example, this region in such a way that eventually we will arrive at the maximum value. This is something like that root finding algorithm. Okay, in your root finding algorithm, what we do, if your root is there, then we choose two values, say XL and XU there. Then we gradually shrink that value in such a way that we will arrive at this thing again. We use a bisection algorithm earlier. Can you remember?
Yes, sir.
Yes, sir.
That means in each step, you can choose your shrink your value to half. But in the optimization technique, actually, this technique is called search technique, search method. In the search method, actually, we can have some other improved version of bisection technique so that your algorithm can be converged, or it will take lesser calculation to obtain the maximum. In this way, we can proceed with search algorithm. We'll be discussing more elaborately with regard to text later. Okay, just general discussion. Another issue is that if your FX is not, for example, so easy to be proceeded with calculating find the maximizer or minimizer point, then what you can do, you see that our case is what? At the maximum or minimum point, the derivative of the function fx dx should be equal to 0, isn't it?
Yes, sir.
Okay, if this is your 0, then that 0 can be calculated if your fx is available to you, like what you have done for your power calculation PL that was available to you, and you can easily differentiate it and you solve for RL. But if that value is not, for example, so easy, or it can be transcendental type so that it cannot be solved so easily, then what you can do then? You can check, for example, this, you can just consider this derivative as another function gx. Then dx equal to 0 become your problem. Is it not a root finding problem?
Yes, sir.
Yes, sir.
It will be a root finding problem. If it is a root finding problem, then we can use even bracketing technique again there to find the root, or even you have your Newton method or second method, isn't it? That you learned earlier.
Yes,
You
sir.
can use this to find your technique. Find your find your maximizer point. Okay. So in this way, actually, we will proceed in this introductory lecture. In your level, we will be confining with our one-dimensional unconstrained type optimization only. Nowadays, in the intermediate level syllabus, you have your linear programming type problem there. Have you? Did you just see it in your intermediate math?
Yes, sir.
Yes, sir.
So this is another solution because in this case you see that a multivariable problem. Probably in your level only two variables are there, isn't it? Then some functions you need to find the optimum values. If some constant functions are there, graphically you can do that. So this is also a technique, but unconstrained type numerical optimization technique is widely used in our electrical engineering in particular. So we'll be discussing the thing gradually. Let me do it with our first search technique, okay? Okay, your search technique, you see, probably I did not share it, isn't it?
No,
Sir,
sir.
এখনো screen share হয়নি।
Okay, I will be concluding my lecture within 10 because I cannot talk that much because I am exhausted. So I will finish this thing today at this point. Actually, you see that this is a problem of maximization, isn't it? Can you see figure 13.2?
Yes, sir.
It is a maximization problem. Your lower end and upper end is bracketed. And our thing is that you have to find the intermediate point in such a way that we'll be reaching at the maximum. One of the technique is called golden search technique, golden section search. So that golden section search is actually has a historical in nature. You can find some history of golden ratio, or in that book some thing are also there. You can take a look. So that the algorithm is very simple. The original length between XU and XL, that means your XU minus XL is equal to L0. That is divided into two sections. One is L1 and another L2 in such a way that equation 13.2 will hold. If equation 13.2 will be holding, then and we replace our L0 by L1 and L2, we will be obtaining an equation 13.3. In that 13.3, the ratio L2 divided by L1, of course, this ratio will be less than 1, is represented by a factor R. Then we will be obtaining an equation 13.5. You can easily solve for R, the 13.5 is equal to 0.612. This quantity square root of 5 minus 1 divided by 2 is called golden ratio. Okay, yeah, this has some application also in your computer programming. In your first year computer programming, haven't you learned about some recursive algorithm?
Yes, sir.
Recursion like calculation of factorial.
Yes,
or-
sir.
Yes, sir.
Or another, can you give me another example? Some sequence, Hanoi Tower,
Yes, sir. Tower of Hanoi.
Tower of Hanoi or Fibonacci sequence.
Yes, sir.
Okay, so you see that there exists some nature because this number is generated in such a way that a new number is generated using two previous numbers, isn't it? So in this way, actually, this ratio is there. What we can do, if that ratio is with us, that in our root finding cases of bracketing technique, we shrink the search window by halving it, but here it is not halved. It will be shrink by a factor like golden ratio, okay? How it is implemented, let me discuss it. Okay, the history of golden ratio and Fibonacci numbers are there. You can have a look. Okay, without going to these equations, let me see this thing there. Okay, now let us just find this equation. Okay, here you see UD. UD is actually a distance that is calculated in this way. You have your golden ratio multiplied by the difference of the window. Then your X, that means this is your left search point. This, okay, this is your left point. This is your lower point. This is the upper point. This is the left side. This is the right side. So we will find two interior points X1 and X2 in this way. Okay, your X1 will be equal to lower end plus D, and your right one would be equal to upper end minus D. At X1 and X2, the value of your function is calculated. If that value is calculated and you see that if this fx1 is greater than fx2, then what will happen? You can easily eliminate one region. Can't you do that? Like your bisection technique?
Yes, sir.
So we can easily eliminate. This is described in the next figure. Okay, you see that your x1 is equal to xl minus d1, xl plus d1, and your x2 was equal to xu minus d. So when your x1 is greater than x2, then you see that the left region from x2 to xl can be eliminated. Then you will be left with the region. Then you can proceed with again subdividing the new region by using the same algorithm, and eventually you reach at your optimum value. An example is there. You try to solve this example by your own. And if you feel any problem in understanding this thing, let me know it. Inshallah, I will try to clear it in the next day. Then we have another technique there. We'll inshallah discuss this thing in the next class, and we'll later classes will be review type, and I will review some electrical engineering problem of ODE and other cases, inshallah. And I am planning to take another class test for you, and it will be on PDE, okay? And let me know when you can attempt this. That's it from my part today.
Sir. Sir, can you hear me, sir?
No.
স্যার আমার স্যার অনেকদিন ধরে স্যার একটা কোয়েরি ছিল স্যার, সেটা হচ্ছে স্যার ধরেন একটা কার্ভ যখন স্যার আপনার স্লোপটা যখন 0 হয়ে যাচ্ছে তখনই তো আমরা ম্যাক্সিমাম অথবা মিনিমাম পয়েন্টটা পাচ্ছি, কিন্তু স্যার আমরা যেরকম স্যার ইলপোজড কন্ডিশন দেখেছিলাম স্যার স্ট্রেট লাইনের, ওরকম যদি স্যার হয় যে ক্লোজ টু ফ্ল্যাটনেস, তখন স্যার কিভাবে কি করব?
তখন তো ওই একই প্রবলেমই হবে। তখন ওই প্রবলেমগুলো হ্যান্ডেল করার জন্য আলাদা অ্যালগরিদম আছে।
আচ্ছা স্যার,
ঠিক আছে। তা আমি এই মুহূর্তে আর পরে আমরা ডিসকাস করবো না এটা নিয়ে, হ্যাঁ?
জি স্যার, ইনশাআল্লাহ।
আমরা তুমিও একটু ডিসকাস করো, আমিও একটু দেখবো যে এই প্রবলেমগুলো এইখানে ওইভাবে বর্ণনা করা নাই, তো আমি একটু পড়াশোনা করি।
আচ্ছা স্যার,
ঠিক আছে, তুমিও করো। ওকে, থ্যাংক ইউ।